Flipped Classroom video for Maths AS Unit 1, the Binomial Theorem. So what is the Binomial Theorem? Well, the Binomial Theorem is a way of finding out what we get if we have two numbers or expressions added together and then raised to a particular power. And we're going to look at it for the natural numbers, so we're going to look at things like a plus b in brackets to the power of n, where n is a natural number. The natural numbers are the numbers 1, 2, 3 and so on. N, that symbol there, means the natural numbers, so that extra line is often used for sets that are describing particular sets of numbers, and that is the set of numbers 1, 2, 3 and so on, and the theorem can be expressed as it says there, and that's from the WJC formula booklet, and the N1 and then N2 and so on in brackets like that you'll remember from the video about combinations, and you work on combinations and permutations. That is NC1 and then NC2 and so on. And we'll have a look at the first few expressions there. So if we have a plus b to the naught, that would just give us 1, as we know. If we have a plus b to the power of 1, we know that that is 1a plus 1b. If we have a plus b squared, that gives us 1a squared plus 2ab plus 1b squared. And if we have a plus b cubed, we have 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And we can see building up there is Pascal's triangle. And it's interesting to see how this works with Pascal's triangle. Why does Pascal's triangle work here? Now remember also with Pascal's triangle that we can build that using the idea of combinations, and that explains why we've got those combinations in the formula from the WJC booklet at the top there. Okay, so let's see how we get 1331 from 121. Well, a plus b cubed is the same as a plus b squared times another a plus b. So first of all we'll multiply out a plus b squared, which gives us a squared plus 2ab plus b squared, and we'll need to times that by a, and we'll also need to times it by b. So I've written that out separately. You wouldn't have to write this out separately if you're doing this as part of a normal piece of work, but this is for illustrating what's happening. So when we times by a, then we get a squared times a is a cubed, and 2ab times a is 2a squared b, and b squared times a is ab squared. And then when we times by b, we get a squared b for the first term, we get 2ab squared for the second, and we get b cubed for the third. And you can see now why I've written it like that, and it's to line up the terms that are the same type. So the a squared b and the ab squared are lined up. And that then gives us our a cubed plus 3a squared b plus 3ab squared plus b cubed. So if we look at that on Pascal's triangle, if we put our a squared, ab and b squared on the relevant row, then if we think of multiplying to the left, as it were, or diagonally to the left by a, then that gives us our a cubed, our 2a squared b and our ab squared. But if we multiply going to the right, we get a squared b, 2ab squared and b cubed, and then we can see that they add up as before to what we want for that line. So that's where the 1331 is coming from, and we can see how that would work carrying on down the triangle. The practical point of this is that for small values of n, it can be quicker to use Pascal's triangle to find the coefficients. For larger n, it's quicker to use NCR, and as previously mentioned on the calculators, that's the NCR, which is on the divide button. There are also situations where n is unknown, and we need to use NCR as a formula in those cases as well. Notice, by the way, the similarity between the expression for the binomial theorem, which we've got here, and the expression used for binomial distribution probabilities. You may have studied that already, you may study it a bit later on, but whether you study it already or later, then do notice that this is essentially the same formula. Okay, let's have a look at some applications. Sometimes we just need to expand a bracket. It just comes up in some algebraic situation, we just need to expand it and get on with it, sort of thing. So if we have 2 plus 3x to the power of 4, then for this Pascal's triangle is quick. Because it's to the power of 4, we can just use the 1, 4, 6, 4, 1 row, and it's, even if you can't remember it or don't trust yourself to remember it, it's quick enough to write that out. And that means we have those green coefficients there, 1, 4, 6, 4, 1 on that line, and we just have the first term to the power of 4, then the first term to the power of 3, and the second term to the power of 1, then both to the power of 2, then 1 and 3, and then 4. And so you can see how that builds up. And then you have to do the sums. I've written them out bit by bit here. So the 4 times 2 cubed times 3x to the power of 1. We've got the 4, we've got the 8 for the 2 cubed, we've got 3 from the 3x, and so on. In practice, you'd probably just whack those numbers into your calculator to get them. But in the end, anyway, it works out as 16 plus 96x plus 216x squared plus 216x cubed plus 81x to the power of 4. To make sure you got it right, a quick way of doing this is we could put the number 1 in. So if we put x equals 1 into the original expression of 2 plus 3x to the power of 4, that gives us 2 plus 3 times 1, which is 5 to the power of 4, and that's 625. And if we put that in our expression that we've worked out, then with x equals to 1, all we have to do is add up all those coefficients, and sure enough, they come to 625. So there's a fair chance we haven't made a slip there. For finding some terms, in some situations, if the power is large, then combination values are better. So, for example, we might be asked or need to find the first 4 terms of 1 plus a half x to the power of 10 in ascending powers of x. So that's ascending means the first 4. We could write out Pascal's triangle down to the 10th row. In fact, we'd only have to do the first 4 numbers of the 10th row, but that still would take quite a while. So it's better to use combinations. So a plus b to the 10 is a to the 10 plus 10c1 a to the 9b plus 10c2 a to the 8b squared plus 10c3 a to the 7b cubed plus ... And we only write the ones we want, and writing it in an abstract form like this is very good for avoiding slips. It's not essential, but I'd say it was my advice, at least when you're coming to terms with and getting used to writing this stuff. So a and b are of course 1 and a half x from our question, and we're going to the power of 10 as before. So 1 plus x over 2 to the power of 10 is 1 to the power of 10 plus, well, 10c1 is 10, and we can get that from our calculator, and that's 1 to the power of 9 and then times x over 2. 10c2 is 45, again we can get that from the calculator. You can do it easily enough in your head as well, because 10c2 is 10 times 9 divided by 2 times 1, which is 90 divided by 2, which is 45, but no shame in using the calculator. So that's times 1 to the power of 8 and then x over 2 squared, and then 10c3 is 120, and that's times 1 to the 7 times x over 2 cubed. Notice the plus ... That's making clear that we know that's not the end of it, but we've only been asked for the first 4, or we only need the first 4 for some reason, but we're making clear that we know that there are other terms. The other thing is writing 1 to the 10, 1 to the 9, 1 to the 8, 1 to the 7. Again, you could just write 1 for the first term there, and you could not even bother writing it for the others. But in terms of checking back and just making sure that your working is very clear, and in terms of good habits, then it's probably a good idea to include them. Once we've done that, we can tidy everything up. So we have 1 plus 10 over 2, so that divided by 2 comes from the x over 2. In the next term, 45 over 4 comes from the 2 squared. And notice that all of those x over 2's have been bracketed because it's very easy to forget to square or cube those 2's on the bottom there if you don't put a bracket there. It's mathematically incorrect if you don't put a bracket there as well. So then we cancel everything that we can and we get this expression, which is as simplified as we can do. Now we might be happy with that, but it's still worth checking it if we can. And a good way to check it is, if we notice the powers are going up, if we use a very small number, so for example 0.01, then the terms that we haven't bothered with, so the x to the power of 4, x to the power of 5, x to the power of 6, and so on, they would be way down in the decimal places. 0.01 to the power of 4 is 0.00000001, and even more noughts for the higher powers, so they're not going to impinge on the first few decimal places. So if we put the expression 1 plus 0.01 over 2 all to the power of 10 in the calculator, so this is the actual answer, then we get that number there, 1.051140. If we put 0.01 into our expression, so I've just started the writing of that, it's 1 plus 5 times 0.01, it would then be plus 45 over 4 times 0.01 squared, and then the other term with the x cubed, and that matches to 5 decimal places, and that suggests that we've probably got all our coefficients right for that question, the 5, the 45 over 4 and the 15. If any of them were wrong, then it would have shown up in those first few decimal places. So that's a good way to check.